Hello. The purpose of this video is to review over content that you can expect to see on your upcoming exam, Exam 2, which covers parts of Chapter 4, 5, 6, 7, and parts of Chapter 15 that go over the way rainbows work. Going back to a couple weeks ago, our focus was on moisture. We talked about humidity, dew point, uh, the way condensation works, and the formation of clouds, precipitation. So if we can talk a little bit about that now, we can cover some of the main ideas. So humidity is a measure of the amount of moisture in the air that air is able to hold. And we know that humidity depends on two things. The amount of moisture, amount of water in the air, and also the air temperature. So it's clear that the humidity will increase the more water you put into the atmosphere. All right? But the air's capacity to hold water depends on the air temperature. Air temperature that's higher, if the temperature of the air is high, the air is able to hold more moisture. So the air expands, and you can think of there being more space available to fit water molecules. So the air's capacity to hold moisture increases with air temperature. So let's look at an example. Here I've provided some data about a couple of cities. City A has a temperature of 90 degrees, so does City B, and City C has a temperature of 50 degrees Fahrenheit. So City A and B are much warmer than City C, and so therefore, because the temperature is higher, the air is able to hold more moisture in those areas. So City A and B have the higher capacity to hold more moisture than City C. But then if you want to talk more about humidity, then we need to know a little bit about dew point. And dew point is the temperature you would have to drop the air down to in order to reach saturation. Okay, so you can do that by either you can reach the dew point by either adding water or lowering the temperature. So if we assume that the amount of moisture doesn't change, then the temperature is fixed for the dew point. So the air temperature would then have to drop to the dew point temperature in order for the air to reach saturation, and for there to be 100% humidity at that point. So if you add more water into the air and don't change the temperature, the dew point will go up. So you can still reach saturation if the dew point goes up, but that's done by adding more moisture. So I've mentioned here in our example that City A has a dew point of 60 degrees, B has a dew point of 80 degrees, and C has a dew point of 50 degrees. So if we had to guess where, at what city there was the most moisture in the air, we would have to say it'd have to be City B. Why is that? The closer that the two temperatures are to one another, the higher the humidity. So you might look at City C, where it says that both the air temperature and the dew point are 50 degrees. So what can be said about that is that it's 100% humidity there. That means that the atmosphere there has reached the point where it can no longer hold any more air, any more water, and therefore it um, uh, will condense out into either fog or um, mist, um, depending on the conditions of the atmosphere in that area. But city B, with the higher temperature and the high dew point, hasn't quite reached 100% humidity, but it's getting close. And because of the higher temperature, you know that it's harder to reach 100% humidity because you need more water than you would have in city C. So it is likely that in city B that the atmosphere is holding more moisture at that time. So it would be very unpleasant to be there in city B. So despite the fact that it's not 100% humidity, I would rather be in city C with 100% humidity. You won't feel the humidity as much as you would in city B, because ultimately what we feel is the total moisture in the air that gives us discomfort. When there's a lot of moisture in the air, then it really makes us uncomfortable. And so even though city C is unable to hold any more moisture, it wasn't able to hold much to begin with because of the lower temperatures compared to cities A and B. City A has a lower dew point, so it's not that uncomfortable, but the temperature is still high, so you have to deal with that. Continuing with moisture, we can talk about condensation. So when the vapor that's in the air cools, the gas of water vapor releases heat into its surroundings, and the water molecules condense to form liquid water. And if they condense onto a surface, like it would in the morning when the air temperature goes down, and you've reached the dew point, then we call that is dew. And if the temperatures when the dew point is reached is below freezing, then what you get is, instead of liquid water dew, you get frozen water frost. Right, that's the difference. But we had talked about cloud formation and the need for a condensation nuclei, some little speck of dust for water droplets to then coalesce and form into larger droplets. When clouds form near the ground, you get fog, and so we talked about different types of fog. And since fog is a product of reaching the saturation limit, we could talk about fog in the same way that we were talking about humidity. You know, how do you form fog? We have to either cool the air temperature down to reach the dew point, or you have to add more moisture into the air so that you lift the dew point to the air temperature to reach 100% humidity. So the different types of fog are based off of those two principles, either cooling the air down or adding moisture to the air. So in cooling, you have your radiation fog. That's just the earth releasing that infrared and the surface just cooling down. And just through natural cooling, the air temperature reaches its dew point and you form fog. And advection fog, that is when you have a cold surface, like over here, and warm, moist air sitting over top of this warm water, and you get a uh, onshore wind that drives that warm, moist air over that colder surface. So, in order to reach equilibrium, the temperatures to reach the same temperature, um, warm and hot energy always flows from hot to cold. So, the warm temperature, the warm air will try to heat the cool surface, and in turn will cool the moist air down, and by cooling the air, that allows for the fog to form. Um, the upslope fog is another example. You have the moist air being driven up the mountain, where by going up towards the top of the mountain, the air cools. So again, all three of those forms of fog are cooling processes. Then the other process to form fog is by adding moisture into the air. So here you have a geyser. The geyser throws up all this water into the air, and just in that vicinity, the air reaches saturation, and you see the fog being formed. So that's either called evaporation or mixing fog, and you could have a frontal or rain fog that happens after a storm. It rains, and so therefore you have more moisture in the air, and once the rain stops, fog can form. The next item here is cloud types, and so you do need to know all the different cloud types, but we've talked about how they're classified based on their appearance and their height above the ground, and whether or not they make moisture or not. So let's review which types they are, and hopefully this will be helpful. So we're going to separate the different heights into high, medium, and low. You can see that all the high clouds have a cirrus or a cirro in the name. Now, cirro generally means sort of hair-like, wispy. So all of these clouds, because of their altitude, are made up of ice crystals. So it's so cold up there that the droplets have frozen. So you would not get any precipitation that would reach the ground from these types of clouds. They're too high up, and it's hard to hold moisture up here because it's so cold, and whatever moisture is there is frozen. But you can see that the hair-like strands are the cirrus clouds that can be found up there. The very thin sheets that can produce a halo around the sun are due to cirrostratus. Remember, stratus means layer. So just like the stratosphere was the first layer discovered on top of the troposphere because of the temperature inversion, stratus means layer. So you have a layered cloud. It's very thin, and when it passes over the sun, it almost forms a little coating that produces a halo. And then the cirrocumulus. Cumulus means fluffy or pile-like. So they're clumps. They have some thickness to it, whereas the stratus are basically very thin and layered. The cumulus are thick and bumpy. So you can see the contrast. So here you can see the shape of the space between the cirrocumulus clouds, whereas the cirrostratus is just one sheet. And then where you can see these strands, those are the cirrus clouds. Then you drop to the mid-altitude clouds, and again, alto gives us the designation for the middle layer of clouds, and we're going to use the cumulus for fluffy, pile-like, and stratus for layer. Um, Again, no moisture from these clouds either. So these altostratus will usually be very thin but expansive without much breaks, um, and not much waviness to it. It's very, very sheet-like, whereas the alto cumulus will have, again, the bumpy clump-like appearance, typical for a cumulus type of cloud. And then closest to the ground, we have the um, pure stratus cloud. So these are the sheet clouds that are closest to the ground. Now they can occasionally produce some moisture, but not very much. The steady precipitation can come from what we call a nimbostratus. Nimbo typically means storm, so you're going to produce rain with a nimbostratus for sure, and it's usually a persistent, but not like severe rain, but it is continuous. Um, but it's not a cloud that you would expect to see thunder or hail. Um, so that would not be falling from a nimbostratus cloud. You would not see thunder or hail from that type of cloud. In order to get hail and thunder and lightning, you need the vertical development. You need a lot of motion in the cloud, and typically the stratus cloud doesn't get too high, and it remains more sheet-like. But nimbostratus has more moisture. It can rain with a stratus, but typically it stays. It's just very overcast at that point. Stratocumulus. So now we're getting into we're starting to break up the layers, and you're going to start to get a little bit more of that bumpy top that we're used to seeing, the pile-like structure of what we would see a cumulus would be formed. The fair weather cumulus clouds here, those are typically due just from clear skies on summer days, just the thermals getting picked up, heating the surface, air rising and condensing into the atmosphere, and when the cool, dry air sinks, it sinks around the cloud, so it usually leaves these open spaces. That's the space available for the dry, cold air to sink back down, and allows for the warm, moist air to be evaporated underneath the cloud base. When you start to get some vertical development, you get the congestus cloud, and that certainly can produce more heavy downpours, and then eventually lightning and thunder. And we can get to the point where we reach the tropopause, and where the temperature goes back up, and that puts a cap. That inversions tend to put a lid on the development of further development of clouds or condensation, and so the top of this cloud produces what we call the famous anvil shape top, and with strong upper air currents, it can take and shear the top of the cloud so that it pulls part of the cloud up ahead, and wherever it's getting pulled towards, that's the direction that it's moving. So this cloud would be moving from right to left, and so this is our cumulonimbus cloud. So that's where you would see typical storms. The other topic is the types of precipitation. So to get a sense of the different types of precipitation, you're going to want to look at the temperature contrast in the atmosphere. We had talked about how most precipitation in clouds start off as snow, and because up in the atmosphere it's cold enough for water to freeze. But as the precipitation falls, it can encounter different layers of air at different temperatures. And so depending on the air temperatures through which it's falling, that will determine the type of precipitation that you're going to see at the surface. So let's look at a temperature profile. So here we're going to have temperature, and this is increasing temperature, and this is height, increasing height. And this dotted line represents the freezing point for water. So that's the critical number that you're going to want to pay attention to. And so this is below freezing, so typically moisture is going to start over here at some height above the ground below freezing, and then as it falls, it's going to the temperature is going to change. So if it follows a profile that looks something like this, right, what you're seeing here is that the temperature goes up, it passes the freezing point, so this precipitation is melted, and it continues to warm up until it hits the ground. So what hits the ground is liquid, and so this profile would represent rain. We could then have, again, I can just to illustrate, we can have it all start at the same temperature. So you can have the same kind of precipitation up in the cloud, but as it falls, it transforms based on the layers of air and the temperature that it goes through. So let's pick another profile that takes us into this warm sector, but then before it hits the ground, it works its way back over to this side. So let's think about what's happening here. So it's here, it's still snow, it's still frozen precipitation, but when it reaches this point, it melts. So for most of its journey down, it's rain, and so it's very close to the surface before the air temperature is cold enough for water to freeze. So it's likely that this precipitation will hit the ground as rain, but because the surface is below freezing, then the rain will freeze on contact, and hence the name freezing rain. So this is the freezing rain profile. Third would look something like this. In this case, again, we start here with frozen precipitation. There's a period while it falls that it does melt, but it goes back to because there's some temperature inversion here. So there's a layer of warm air that creeped in here that forced the frozen precipitation to melt briefly, but because we're still pretty high off the ground, the precip has enough time once it crosses this boundary to refreeze again, and so this precipitation has frozen again, but it has a different structure than it had when it was up in the cloud. So these tend to be little pellets that can typically bounce when they hit the ground, and that's what we call sleet. And for our last profile, we can just draw basically a line straight down. This is precip that falls through cold air that's below freezing the entire time, and that's what we refer to as snow. The next topic on the exam has to do with atmospheric stability. So you need to know the difference between a stable atmosphere and an unstable atmosphere. Also, what are the adiabatic rates? So a parcel of air that's heated at the surface will want to expand as it's heated, and through the expansion it becomes less dense than the surrounding air and will begin to rise. So warm air rises. So if the air that parcel of air maintains its identity, um, and that is to say that it doesn't exchange any heat with its surroundings, then it will, um, if it's below the saturation limit, if it's not completely saturated air, then as it rises, it will cool at what we call the dry adiabatic rate. Now, the rest of the environment will, the air that's settled in will also cool at the environmental lapse rate, and that's just due to the fact that as you go up into the atmosphere, there are it increasingly gets colder in as you go up into the troposphere. So that's just what we talked about in week 1. That's the lapse rate. So, but the air, as it rises, may cool at a different rate than the rest of the atmosphere surrounding it. And so then you want to compare the temperature of the parcel of air that's ascending to its surroundings to determine whether or not the atmosphere is stable or unstable. So typically the difference is that a stable atmosphere keeps that parcel from rising. So the picture that we have looked at has to do with the helicopter as the mechanism that forces the parcel to rise. So we did talk about actual environmental mechanisms that would cause air to rise in certain circumstances, but it's the case where if you take this parcel of air that's at the surface and you force it to go up to a given height, you can see that its temperature is lower than its surroundings, and because of that it's denser, and so it will sink. That's a stable atmosphere. So stability has to do with whether or not the parcel, if forced to begin to lift, will continue to lift or not. So in a stable atmosphere, the parcel returns back to where it started. So that's, we looked at a picture of a stable equilibrium points like we would talk about in physics. This rock is at a stable point at the bottom of this valley. And so if this person disturbs this rock, it will always, even if it goes back and forth, it will always return back to this location. So if he places it here, it will stay there. So that makes it an equilibrium point. But it's a stable equilibrium point because if it's disturbed, then it will return back to that location. So that's analogous to our air parcel. If it's disturbed, if something lifts it up, something pushes it to rise, whether it is through convection, through frontal convergence, orographic lifting, via some sort of hill or mountain, then its tendency is to go back to where it was, because ultimately it's cooler and denser than the surrounding air. And so you're not going to get storms typically in a stable environment because there's no lift. Now this is an unstable equilibrium. So the rock here at the top of this hill can balance and stay there. So an object at rest will stay at rest. So there's no reason for this rock to move. But if forced to move, if this person displaces it, then it's a runaway effect. The rock on this hill will roll away from the top of the hill, never to return. And so that's the analogy that you want to get thinking about an unstable atmosphere. If you disturb the parcel in an unstable atmosphere and force it to rise, it will continue to rise. So here we have an unstable environment. So if we lift the parcel to a given height, see at the surface it's fine. All the temperatures are the same. So there's no tendency to do anything here. So that's just like the rock being on the top of the hill. If the air is settled here and it's not being disturbed, then it has no business doing anything. All right, but because it's all the same temperature. But if there was a disturbance, if you know, here the helicopter comes in, lifts it up to a kilometer high, so on its own accord it wouldn't move anywhere. But if it was forced to be lifted to a new location, you can see now that its temperature is higher than its surroundings. That makes it less dense and more buoyant, and it will begin to float on top of the surrounding air, and it just becomes worse. The tendency, the the temperature difference between the environment and the parcel becomes larger, and that gives the parcel a greater tendency to continue to rise. And so that brings that parcel higher up into the atmosphere, where it can deliver moisture to the air, and eventually reach saturation and form clouds and precipitation at some point. Here are those mechanisms that can get the air to move. So, so the air is settled here at the surface, but then heating starts to occur, the daily heating, and that forces that air to rise. And so then there's this circulation that begins because of the motion of the air at the surface. You could have a current that forces air to, otherwise if this was just a flat surface, you might just have horizontal winds. But because this mountain is here, then the air is forced to rise. When you force the air to rise, then you have to consider the temperature differences between the air that's being forced to rise and its surroundings, because it might be different. And so that's when you have these clouds forming. Here you have two air currents that converge at this location, which happens to be a low pressure center, because that's where air is rising, so you're taking some of the pressure off the surface, and you can see that it's raining there. We saw something similar to this this past week with the sea breeze that can occur over the Florida Panhandle. Over that peninsula, you have sea breezes on either side that can bring air on shore and form those typical thunderstorms that they're used to down there. And then along frontal boundaries, where you have the mixing of warm and cold air, that also will force air to rise. So a product of precipitation are rainbows. So with that, we talked about a couple of important terminology processes that occur with types of waves. Like light is a form of a wave. So waves will can reflect and refract. So the difference is reflection is the bouncing of a wave off of the surface. So the wave hits a surface and bounces back. Refraction is that the wave bends, and so the beam of light going through a new substance will bend, slow down, as it enters into that new substance. So the water droplets in a rainstorm, at the right angle, if the sun is at the right angle, it has to be at your back, and you're facing the rainstorm ahead of you. So this is going to typically be closer to sunset, and you'd be looking east as the sun sets in the west. You'd be looking for the rainbow towards the east. If it's in the summer, you'd be looking more northeast. If it was the winter, you'd be looking more southeast. but the sun needs to be at your back, and the water droplet acts as as like a prism would to a beam of light. So sunlight is typically white light of all the colors of the rainbow. So when all the colors of visible light strike your eye at once, you see white. Um, so the only time you can see the separate colors is if only those specific portions of the visible spectrum hit your eye one at a time. So if you see that something's red, then you're only getting red light coming in, and that's only one type of wave. Sunlight is made up of many waves coming in packets together, so you're getting all that information all at once. And so when you get that white light hitting your eye, you can't distinguish between red, yellow, violet. So they're inseparable to your eye. But when light passes through a glass, or in this case a water droplet, it will split into its many colors, because the light, depending on the color of light, that's associated with a different amount of energy, and depending on the energy, that determines the speed of that light in a medium. I think we had talked about in class that light never actually slows down, that the speed of light is the speed of light, but the speed of light in, let's say, water appears to be slower because of the light's interaction with water. So the water does a job of absorbing light and re-radiating it inside the droplet. So it's all going on, and ultimately that takes up some of the time that the light would normally take to travel. So the light's either moving or it's not moving. So if you see that light is slowing down, then there must have been periods in the motion where the light was absorbed and then re-radiated and absorbed again and re-radiated. But what we see is the overall effect. So we see the light coming in, and all the colors of the rainbow will then split up inside of the droplet, and then it hits the back wall of the droplet, and this is where what we call reflection occurs. So first of all, I should say that when it crosses this boundary, you get refraction, so the bending of light. So you can imagine if this droplet wasn't here, then it would go off in a straight line, and so that's where it would be over here. The red light appears to bend less. The purple light appears to bend more. So you would say that the purple light's been refracted more than the red light. But they both bounce off the back of the droplet, and that's reflection. And then they are bounced away from the back towards the front, where they bend again and come out as separate waves of light. And so only one of these beams ends up striking your eye. And so for you to form the vision of a rainbow, you have to see multiple droplets to reach your eye. So you'll get a red beam of light from one droplet, and then there's others that will deliver orange and yellow, and it will complete the rainbow for you. But each color is coming to you from a different droplet. So that's why we said that everybody gets a unique rainbow that only they can see, because everybody's going to see through different droplets. Where we said there was the double rainbow, you can see that the secondary rainbow here is dimmer, and the colors are inverted. And that's due, if you look inside of the droplet, to a secondary or double reflection that's going on here. So the light bounces twice within the droplet. So when that happens, some of the energy is lost, so it becomes dimmer, but it also inverts the colors upside down from what the primary rainbow will look like. The last major concept is the concept of pressure. That again was introduced back in the first week when we talked about atmospheric pressure, and that's the force of gravity acting on the air over a given area. So with the entire weight of the atmosphere pushing down on the surface, you can measure atmospheric pressure to be somewhere a little over 1,000 millibars. But daily air pressure changes because of the heating, unequal heating of the Earth's surface. So you may remember a illustration with the buildings. So pressure is dependent on the amount of stuff in its environment and the force acting on that stuff, because we're talking about gravity. So gravity is the force that we're considering when we have to worry about air pressure. So these two columns of air are at the same temperature and contain the same number of molecules, so that makes them the same pressure. Gravity is acting on these columns the same, and so as you go up, the pressure is decreasing, because if you take this layer right here, you can count 1, 2, 3 rows of these dots, and so the weight acting on this area here, on this row of dots, is only the weight of these 3 top rows, and so that pressure is less when you compare to this layer. If you look at this layer, then you got 1, 2, 3, 4, 5, 6, 7, 8 rows of dots, and so that's extra weight that's pushing down on this layer of the atmosphere, and so there's more pressure here. So gravity is exerting a larger force on this area at this altitude, but as you get to the surface, you expect it to be the highest pressure. Now, if you look at these two columns of air, there are the same number of rows of dots. So that means each of these columns contains the same amount of stuff. So there's the same weight pushing down on the surface in both columns. So at the surface, you have the same pressure. But what a heated column does is it expands. Colder columns cool and contract, they condense, get closer, compacted. So this pushes air up higher into the atmosphere. So when we're over here and comparing, the pressure at this level, let's just say, you have 3 rows up here, you have 3 rows up here. So at this 4th row of dots, the pressure is the same, so there's no motion of the air, and at the surface the pressure is higher, but it's the same. Here the surface at the pressure at the surface is high and equal, but now you get a difference. So let's go to this second to last layer here. So at the second to last layer, you only have 1 row of dots in this column of air. So the pressure here is dependent on how many rows of dots that we see. So there's only 1 row of dots, so the pressure is very low. We're forgetting the rest of the environment for right now, but just for comparison here, the pressure on this column of air at this height is just the weight of this first row of dots. But at the same height around here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 rows of dots. So clearly the pressure is higher at the altitude, at this altitude, than it is here, because you have all of these rows of dots ahead. It doesn't change the pressure at the surface at the beginning, because the column of air is ultimately still here. So when we're looking, making this observation, this column of air isn't moving yet, and neither is this one. But when you get this pressure contrast, you get what's called the pressure gradient force. So when you have along a horizontal, if you look along a straight line, left and right, if there's a pressure difference, then there's the tendency for air to flow from high pressure to low pressure. There's a force that the air feels that gets the air moving from high to low. Once that air movement begins, then that's going to take some of this air out of this column and put it into this column. So what happens at the surface, now there's going to be less weight in this column, so that's going to drop the pressure here, and then you're going to put more weight, more rows of dots into this column, and that's going to increase the pressure there. So ultimately that's what you start to get when you heat the surface. Low pressure develops at the surface because air begins to rise, and it's able to because at higher altitudes all that air that's being forced up creates higher pressure aloft, which forces it to spread out and diverge away from that column towards areas of lower pressure that surround it. But in those areas of lower pressure aloft, air becomes more dense and begins to sink, and that creates higher pressure at the surface. So now at the surface, what happens? At the surface, you have at City 1 high pressure. City 2 is low pressure. So now you're going to have a horizontal movement of the air from City 1 towards City 2. And that's what the people in these cities would feel as wind. So wind is nothing more than the motion of the air due to unequal heating of the Earth's surface, where the air is forced to move by a pressure gradient force. So let's go through this process one more time. So the surface here is being heated, so the air begins to rise. Where the air lifts up from the surface, it forms low pressure. But all the extra air that we're pushing up into the atmosphere forms high pressure. The air diverges away from the area of high pressure towards areas of low pressure. So along that same altitude, there is an area surrounding the high pressure aloft where there's areas of lower pressure. Now, the column of air beneath the low pressure zone aloft is becoming more dense and sinking, and so the air begins to sink at this zone, and all the added weight at the surface forms high pressure. And now we have a pressure difference along the surface where we have high pressure to the west and low pressure to the east. And so now we are going to get air to flow along the surface from west to east. So we would call that a westerly wind. So winds out of the west flowing to the east. And so this is driven by the pressure gradient force. The pressure gradient force was also responsible for this motion here. The pressure gradient force always gets air to flow from high to low. So not to be confused with the vertical motion. See, this is horizontal, this is left and right at the same altitude, whether it's on the surface or aloft. You get something different vertically. See how this arrow looks like it's going from low to high, but the air is not flowing upward because it's trying to travel to areas of higher pressure. The result, so the air was already flowing, it was forced to flow that way, and as a result increased the pressure in that zone aloft. All right, so why did this arrow form. That arrow formed because we were heating the surface, and that surface heating created convection that allowed for that thermal to rise up. So otherwise, that without that heating, the air would not have risen. And similarly, the air here, again, it looks like it's going from low to high, but the air would not want to sink down. It's denser, and so it's heavier, and so this is gravity doing this work. So gravity, like all things, makes objects fall. So it's the air's moving from this low pressure to high pressure, not because of the pressure gradient force, but because of the weight of the air and gravity's pull towards the Earth. So this is the lift from the heating that gave this column of air enough energy to rise, and this is because of gravity pulling the column of air down. Now, this process explains things like sea breezes and land breezes. All right. So the sea breeze, what we could say during a sea breeze is if you would get, if this is the ocean and this is the shore, then this would make sense for a sea breeze. So if we want to look real quick why that's the case, so the sun being out will heat the surface of the Earth pretty evenly, at least in this area if there's no clouds or anything like that. But the shoreline, the land will re-radiate that heat much quicker than the ocean will. And so the overall effect is that you have more air rising over the shore than over the ocean. And so you get this convection that happens that takes air up off the shore towards the ocean. It sinks over the ocean and then pulls air from the ocean onto the shore. So the moving onshore winds off the ocean are generally cooler winds, and that's what keeps the shore cooler during the day. That's what we call the sea breeze. And now if we just reverse this, I'm not going to reverse the cell, I'll reverse where the ocean and the shore are. So this is a daily cycle. So we had sea breezes during the day, and then at night the tables turn because the sun is gone, and so now the land really doesn't have much in the way of heat left over. So now this is going to be where the ocean is, and here's the shore. It's over here. So now the overall net effect is that air over the ocean rises, because whereas the shore has pretty much expended all that heat from the day. Now the sun's not out, so it's not absorbing any new heat. The ocean has done a better job of keeping that heat trapped, and so it's letting it off slowly, and so there's more heat to be released, and so you get more vertical movement of air over the ocean, and then it drifts onshore, sinks onshore, and then drives in air offshore. Right? So there's a offshore wind where it's going onto the ocean from the shore, and that typically is a dry, warmer air, and so that keeps the temperatures from dropping all that much, and we call that the land breeze. Now, because of the Earth's rotation, we get the effect that we call the Coriolis force. This is not a real force, but it is what it appears it appears to be have the same effect as a force acting on an object in normal circumstances, but what's happening here is the Earth rotating, and so the Earth is rotating faster at the equator than it is at the poles. So anytime you try to get something moving across latitudes from the equator towards the North or South Pole, then as it tries to move in a straight line, because objects in motion stay in straight line motion unless acted upon by forces. So in reality, those objects do try to maintain straight line motion, ignoring friction, but still from our point of view, they look like they make a turn, or they're deflected, and that's because of this Coriolis effect. So we call it a Coriolis force because rather than thinking that we're on a spinning Earth, we can sort of make up this fake force that at least gives us a better way of visualizing the overall effect. So we know that the force doesn't really exist, but by thinking about it as like a force, it helps us to ignore the fact that we're on a spinning Earth. So the consequence to this is that if you're if you're in the northern hemisphere, objects are deflected to the right of their paths. So you get that effect there. So both of those arrows show a deflection to the right of their path. But in the southern hemisphere, objects are deflected to the left of their path. Now you can notice that if you're whether you're going from the North Pole to the equator or the South Pole to the equator, you can see that the arrow direction is from east to west, basically. So, or out of the north or southeast. So it's more of an easterly wind generated by the Coriolis effect if you're heading towards the equator. If you're heading away from the equator in either direction, then you get a westerly direction, so from west to east, and that's the same case for both north and southern hemispheres. But just to illustrate the point that we brought up a couple times in class about how the Coriolis, the effect of all the forces, the pressure gradient force and the Coriolis force, what impact they have on the motion of a parcel of air. Let's again consider we have these isobars in black here. They represent lines of equal pressure. So we can say that perhaps this is 1,000 millibars, this is 996, this is millibars, and this is 992, and this is 988. So it is clear that the pressure is dropping if you head from this isobar to this isobar. So it is also then clear that we can label up here as a region of lower pressure, and down here a region of higher pressure. So if we get a parcel of air to start, let's see, down here. So this is our air parcel. Then it immediately feels a force from the due to the pressure gradient force, and that's because there's a difference in pressure. So horizontal difference in pressure. So like this is like a satellite view. So you're looking. This is not vertical, because if this were vertical, if this was like the ground and this was higher up, that the air still would not rise unless, because there could be a pressure gradient upward, but then the force of gravity oftentimes will balance it. You'd have to heat the air and make it less dense to get it to start to rise. Otherwise, it'll just settle at the surface because of gravity. But this is horizontal. Pressure gradient forces are usually something we consider horizontally. So this could be a loft, but we're looking sort of top-down view of this. So this is a horizontal change in pressure. So immediately it feels a force towards the low pressure, and it's always going to be across perpendicular to the isobars. So it's always going to cross this force is always going to cross that the isobars at a right angle. So the red arrow represents the pressure gradient force. So with that, the air parcel, we talked about Newton's second law, that a force causes an object to accelerate. So that means that if the parcel was not moving, it's going to start to move. It's going to accelerate, so that means its speed will change. So it's picking up speed. So now it's moving. It moved up to this location. Now, at this time, because it's moving, that means that there is another force present. You not only have the same pressure gradient force that was present before. The pressure gradient force is going to remain the same strength here because I've tried to keep my isobars split up pretty evenly. If they were to get closer, my arrow would be longer, but I'll keep them relatively the same. But now, because that was its general direction here at the beginning, now you're going to get what we would represent as the Coriolis force coming in, that I'll draw in blue, and it's going to, in the northern hemisphere, get the object to deflect to the right. Now, because we're just starting out, the Coriolis force arrow will be small, and that's because we're still just picking up speed. Now, adding these two arrows together gets you the resultant, which is the direction that the parcel will move at this point with these two forces interacting with it. So it's going to move up a little bit this way, and it's going to move over a little bit this way. So the overall effect is that it's going to move in this direction. So now when that'll determine where I draw my box here for my parcel next. Now it's here, right? Because here it was just moving straight up this way, but now it's going to move in this direction. So now we draw our arrows again. We're going to have our pressure gradient force still across the isobars this way, and now I'm going to consider this purple arrow, and let me just temporarily move it this way. This is the direction that the box was moving previously. I say the box, the parcel. So when we draw the pressure gradient force, sorry, the Coriolis force. The Coriolis, so we have the pressure gradient force here. When we draw the pressure gradient force, it's going to be at a right angle to this. It's going to, so the box, the parcel's feeling as if it wants to move in the direction of the purple arrow, but now it's sensing that there's this other force present that's trying to get it to go to the right of its path. And now I'm going to try to draw that longer than it was before. And now we're going to draw a new purple arrow to represent the new motion caused by the two forces here. So that was the original, and we'll get another purple arrow. So actually, to determine that, I'm going to shift this red arrow here, and this is called tip to tail method for adding these arrows. And so this is now my new arrow. And I'm going to move the red arrow back. Alright, so that's its new direction. Alright, so now if we're trying to ask where's the parcel going to be now, it's going to be here. So you can see that its rate, its upward progress has diminished, and now it's gaining more motion to the right. So now let's complete this process here. So let's bring back the red arrow. Red arrow is still going to be pointing towards the low, and if I bring this over, we can draw the blue arrow. So it's going to remain 90 degrees from this, and we're going to make it a lot bigger now. Alright. And let's do tip to tail. And we're going to draw our new purple arrow. I'm going to return this guy back to where he was. And we'll do a new purple arrow, which is basically almost straight across this way. And we'll return red back to where he was. So now, the tendency for this parcel is to move to the right here. So now its upward motion has stopped. So now when I'm going to do one more, if we draw the arrows here, we'll draw our pressure gradient force. And because now it's trying to move to the right this way, and the Coriolis force is deflecting it to the right of that, that means the Coriolis force is now against the pressure gradient force. And so now what we get is the parcel to just drift this way without any additional turning. And so we can show that. I'm going to put 2 strikes through these arrows. So this is the pressure gradient force, and this is the Coriolis force. And when these two forces balance out, we've then created a geostrophic wind. Geostrophic winds run parallel to the isobars. So they don't typically happen on the surface because friction is a force that cuts this down, the Coriolis force, and so you never get them running exactly parallel to the isobars. But the overall motion, if you sort of connect the dots here, is a rightward deflection by the Coriolis force until the Coriolis force and the pressure gradient force match up. Then there's no more deflection at that point. And finally, what we talked about last week were scales to look at different circulation patterns. So we can define them as small, medium, and large scales. Micro is small scales. They include, what happens in your backyard, down your street, in your local neighborhood. So they can include things like little eddies, those little turbulent rotational air currents that are usually formed by some obstruction, little dust devils, the circulations inside of a smokestack, rain from a single cell cumulonimbus cloud that again could impact your area. It could be raining on one side of the street and dry on the other side of the street. That is a microscale that would most likely happen because of a single cell thunderstorm, cumulonimbus cloud, that is not widespread. It's just very local. The mesoscales deal with more along the lines of you know, citywide rain, um, to statewide. So larger systems like bigger storms, fronts, and then when you get to macro, we're dealing with going out towards hurricane size, um, the patterns that affect the entire United States, and eventually large systems like the global wind patterns, jet streams, ocean currents, things like that would fit under the global patterns. And that's what I want to spend um, a little bit of time reviewing with you are the global winds. And from there you get your uh, pressure zones, an understanding of why certain climates have been established in those regions, and um, how you get certain um, currents that form, whether they be ocean currents or air currents. It's all because of those global winds. We did talk also about some other um, more local situations like the monsoon and various types of winds. That's where we brought up sea breeze and land breeze were more of a micro to a meso scale situation, more micro scale. But you had the Santa Ana winds, the Kiribatic winds in the Arctic, Antarctic, um, the Chinook winds that are the dry winds coming off onto the leeward side of the mountain where it's going to be dry and warm. Um, the monsoons, again in Southeast Asia, you would expect uh, to give them wetter summers because you get that onshore wind consistently throughout that season, which brings in a lot of moist air, which allows for rain, a season of high amounts of rain. And then they usually have dry winters because the winds reverse as the sun angle, the direct rays of the sun begin to migrate to the south of the equator. Um, it brings along the certain wind patterns which allow for a shifting to occur, which changes the onshore wind to an offshore wind, which is generally drier. And so um, the summer monsoon brings in lots of moisture, and in the winter, dry conditions. But let's talk about the global winds. So we talked about the single cell theory, and that assumes that um, there's no um, land-sea contrast, so it's either all ocean or all land, whatever the case may be. We assume no tilt, so that um, you're not getting the seasonal variations in heating. And the single cell also assumes no rotation. And with that, that means that there's no day or night. There's places that are always seeing the sun and places that are always in the darkness. And so that would allow for a steady system pattern to form that would not change over time. And so what that should look like would be heating consistently at the equator, where there's more direct rays of the sun, and very cold, dense air at the poles. And so you'd have all the lifting going on. So low pressure at the surface, high pressure aloft. High pressure aloft diverges the air towards the poles, where it sinks, and where there's lower pressure aloft at the poles. But then high pressure at the surface, where the air is sinking, and then the air pressure, the air flows from high to low along the surface back towards the equator. And so that's just a way for the Earth to try to redistribute the energy it's receiving from the sun. So it's heating and air conditioning unit. But now if we add in a complication to make the model more realistic, we add in the rotation of the Earth. And the rotation then brings about the Coriolis effect, which brings in deflections. It brings in um, the fact that the air will begin to sink at and rise at different latitudes. So, um, so the important latitudes to remember: we have the equator, 30 degrees north and south, and then 60 degrees north and south. And those are not to be confused with some other famous latitudes. For instance, the 23 and a half degrees north latitude is what we call the Tropic of Cancer, and that's the place that you would find the sun directly overhead on the first day of summer. And then you have the 23 and a half degrees south, which is the Tropic of Capricorn, and that's where you find the sun on the first day of winter. And then there's also the other famous latitudes like 66 and a half degrees north. That's the Arctic Circle. That's the point from which above it they get days where in the winter that they don't see the sun, and in the summer days where they get continuous days where there's always the sun is out. And then you have the 66 and a half degrees south is the Antarctic Circle, right? So not to confuse those latitudes. These are the latitudes that we're going to use. And again, this is not a perfect model, but it's a way for us to begin to understand some of the things that we actually see. So this does not take into account the tilt of the Earth. It does not take into account the fact that there's land and water that's distributed differently across the Earth's surface. So, but again, it helps us to begin to think correctly about certain things in these global patterns. So we start with the idea that warm air rises at the equator. That forms our first global pressure zone, a global low pressure zone at the equator. So low pressure is associated with stormy weather. If you look on a barometer, which is measuring pressure, and you see it dropping, going towards lower pressure, you know that a storm is approaching, right? So low pressure is associated with stormy weather. So here it's hot and stormy, so that means that you're going to get lots of abundant rainfall in this zone. So these are our tropics, and specifically the places where you would find the tropical rainforests. The air diverges away from the equator aloft at some altitude, and at the same time we get cold air descending onto the poles, and we get our second global pressure zones. So at the poles we have global high pressure. So high pressure is associated with dry weather. So again, if you look at your barometer and you see that the barometer is going up, the values on the barometer is increasing, the barometric pressure is increasing, that means that clear weather is on its way, right? Now, it's dry and it's cold here. So those are the places we call the tundras, which are essentially cold deserts. As a matter of fact, Antarctica is drier than the Sahara Desert, right? So just because it's cold doesn't mean it's not desert-like. It's drier than the Sahara Desert. But we see all that ice, and you can get the misconception that it's snowing there, but that ice generally has been there for a long time. And once this descending air hits the surface, it also diverges and moves away. And so now here's where the complication begins to show. For our columns of air that have risen at the equator, as they diverge away, you've got, for one, uh, uh, some air that is affected by the Coriolis force. That will eventually lead to a, uh, a the tropical jet stream at this latitude. So this motion of the air here. I'm going to draw another Earth here, um, and I want to illustrate for you what's happening aloft. All right, so not to be confused with what we're going to draw over here are the surface wind patterns. What I'm going to draw over here for you in red are going to be what's happening aloft. So um, these are the clouds that form over the equator where you have this low pressure. So this is aloft. The air is diverging away from the equator, right? And now because of the Coriolis force, the air that's moving away from the equator is moving to the right of its path in the north, to the left of its path in the south. That will generate, just like in our geostrophic wind, how aloft they start to become parallel to the pressure lines. So so these arrows here will eventually become sort of westerly, but again, not happening on the ground. This is aloft, and so this is where we form the subtropical jet stream. All right. So the subtropical jet stream is formed from some of the air getting affected by the Coriolis force and now drifting from west to east. And because of if you think about, and this is information I didn't share in class due to the time, but if you think about an ice skater, when they're spinning on the ice with their arms extended, they are spinning at a certain rate. When they bring their arms in, they begin to spin faster. That's a law of physics called the conservation of angular momentum. And in the same way, because of the change in the rotational speed that the air experiences from going from the equator towards these higher latitudes, in order to conserve angular momentum, the air speeds up. So it's as if, the arms of the Earth move inward like the ice skater. So because the Earth is bulges out at the equator, it's wider at the equator than it is at 30 degrees north. Then from what the air feels, it's very similar to what an ice skater would feel when they bring their arms in. And so that's why these air currents tend to be very fast. Now, the subtropical jet doesn't really tend to affect our weather that much, but it's the jet stream that forms at what we call the polar front that I'll bring up a little bit later. But the rest of the air becomes cool and dense and dry, so that's why it begins to sink. So it never makes its way up to any higher altitude. Some of it does stay aloft, and that's what turns into the polar jet, but some of it begins to drop. And so this cooler, dry air begins to drop at the 30-degree latitudes, north and south. And so we get our second pressure zone on the Earth. The 30-degree north and south latitudes are where you have the subtropical high pressure zones. This is where all the major deserts of the world are going to be found, because these are tropical climates. They're hotter, um, tends to, tends to receive quite a bit of direct rays of the sun, especially in the summer. Um, but it's also dry because of the high pressure that's globally built in. So without the effects, again, we're not considering the effects of your vicinity to bodies of water. Um, any any place around here would develop into desert-like climates. All right, so the Sahara Desert are the places out in the western United States that we consider desert-like, or at that latitude. The Gobi Desert in Asia, those most of Australia, 30 degrees south. Those are your deserts. And then to complete the cycle, now we have um, the surface winds, and the surface winds are driven from high to low due to the pressure gradient force, and they're winds that move from the higher latitudes towards the equator. So, in general, these are this cell in the atmosphere, these are called the Hadley cells. And the winds that appear on the surface are called the trade winds. And again, picking points from the high pressure zones, you then have to consider the Coriolis effect. The air that is moving from high to low in the north is drifting right of its path. So in order to get a clear picture in your head of this motion, then you have to put yourself on this line and look towards this line to see that it's rightward. And then from the 30 degrees south towards the equator, that's in the southern hemisphere, we're deflected to the left. So no matter what, these are easterly winds. So because of the Coriolis effect, and because we're heading in both hemispheres towards the equator, we get winds that generally will develop from east towards the west. So they're easterly winds. So these are called the northeasterly. So if we look at our compass, north, south, east, west, because the winds are coming from this quadrant, right, and they're moving in this direction, it's a northeasterly wind. So northeasterly trade wind. And then these winds are moving this way, so they're moving from the southeast. So these are southeasterly trade winds. Now, the air that we were looking at near the poles that is traveling across the surface reaches latitudes where it heats up. And so before it travels any further, by the time it gets to about 60 degrees north, it heats up enough to start to rise. And so at 60 degrees north and south, we get new global zones of low pressure. And so these low pressure zones have abundant moisture, and it is typically where you're going to find the evergreen forests, pine trees, the ones that are able to withstand cold weather, because it's cold at these latitudes, but they do receive quite a bit of moisture, so they can there's forest that can develop there. So and we'll complete this cell by wrapping it back up here. And these are called the polar cells. and the winds that they produce are easterly easterly winds as well, because you're heading when you go from high to low, you're heading towards the equator. So um, these are called the polar easterly winds. So I've never particularly heard them referred to as the northeasterly polar easterlies and the southeasterly polar easterlies. I just hear polar easterlies as the general term. The last belt uh, doesn't form because of temperature, but because of pressure. So um, along the surface, we have um, the along the surface we have high to low this way, and high to low this way. And aloft, think about what kind of pressure zones we have aloft here. So up here, where the air is rising, we're pushing the air aloft to create high pressure. Here where the air is sinking, there's less air up here, so we're creating low pressure. So naturally then there's a flow aloft from high to low, and so that forms this cell. And again, you have high pressure here, low pressure here, so the flow is this way. So this mid-latitude cell is formed due to pressure differences. We call this one, named after the famous Will Ferrell, not the comedian, the Ferrell cell. And the winds that they produce are winds that move from west to east, so they're westerly winds, and they're important to us because they happen in our latitudes. We are located around 40 degrees north, so this is the latitude that we would want to know more about, because these winds affect our weather daily. So these are the prevailing westerly winds. And so again, we have our right deflection from high to low in the north, and we have left deflection, which is also a westerly wind, in the southern hemisphere. So these are the prevailing westerlies. Now, the air is cold here, and the air is warm here. So where these two winds clash is going to be the development of what we call the polar front. So the polar front is a boundary between the warm and cold air, and that's what where this air is rising here. This is what generates the jet stream, the polar jet, and the polar jet stream is what steers most of our storms around. So here we have, this is called the polar jet stream. And that's what causes our storms to move around the way they do. This polar jet in our summer will retreat to the north. So, I mean, most of these patterns here, like even the are where the trade winds converge. That, remember, that's what we call the intertropical convergence zone, or the doldrums. That line where those winds meet will drift northward in the summer and southward in the winter. And so similarly, the polar jet will retreat northward in the summer and keep all that cold air bottled up in Canada and towards the poles. But then in the winter, it will drop down here. And so um, you'll get situations where, you know, you have big dips in the polar jet, and a low pressure zone will form along that somewhere, and around the low pressure, air that is converging, right? So air is trying to converge towards the low, away from the high towards the low, but is being deflected to the right of its path. And so what the overall effect is that you get a anticyclonic, or I should say cyclonic. It's a cyclone is one that has a counterclockwise rotation. So a counterclockwise rotation around the low pressure. Generally, what that does around one of these systems riding this jet is that it'll start to mix in. Remember, above this jet is cold air, below it is warm air. And this is where you're going to start to get what we call fronts, and this is something we'll talk about next week. You'll get these fronts that develop where you have cold air coming in this way and warm air moving back behind it. And the storm itself will generally move in the direction of the polar jet. So when the polar jet dips down, these storms will dip down. And why that's the case, we'll talk about more later. That's not the focus of what's going to be on this exam, but just as an example of why that's important. The other thing that the surface winds do is stir up the ocean currents. So we have in the northern hemisphere currents of water along the equator moving from east to west. So if you're in the Atlantic, it's heading from Europe, Africa, over towards the Americas. And so if you're on the Pacific, then you're heading towards Asia. And so either way, the water will then encounter the land masses and then get caught by the westerly winds. And what you get are these gyres, these large circulations that are in the north clockwise. So whether it's in the Atlantic or in the Pacific, in the northern hemisphere, these gyres are clockwise circulation currents. So the part of that current, if North America is right here, if the United States is in the middle here, then this current is what we would call the Gulf Stream. That's the warm water that comes right up along our coastline, but it's part of a larger system, this North Pacific gyre that is rotating clockwise. And we have the Pacific gyre, the north. This is the North Atlantic, the North Pacific gyre, which is clockwise. It's counterclockwise in the southern hemisphere. So between Africa and South America, you have the oceans moving in surface currents there. There is a counter current. If you look in your notes, there's a counter current that goes back this way. But again, generally the winds are taking it this way. And so when this current in the Atlantic encounters South America, it forces it to go this way, and we get a counterclockwise gyre in the southern Atlantic. And similarly, when we get towards Australia, we'll get a counterclockwise gyre as well in the southern Pacific. The surface winds are also the reason why we see the hurricanes do what they do. So here's a hurricane that's forming. If it forms in the trade winds, it'll drift towards the west until It's forced up towards the boundary between the trade winds and the westerly winds, and it'll make its famous turn to the east. So the only other thing that we had talked about in terms of global patterns um, was the southern oscillation, which involves um, El Nino and La Nina. So this is something that occurs off the west coast of South America. It's the buildup of warm water. So you get increased upwelling on the west coast of the Americas. That usually happens if this is the west coast of the Americas. We have um, the uh, South Pacific gyre that is counterclockwise. So when that's a strong current, what that will do is, again, you have this is the current here. It'll bring the uh, ocean current up right along the coastline, and so all that mass movement of warm, the sun. It's in the summertime. The sun heats the water on the surface, and all that warm surface water is being moved to an area that is to the northwest of the continent of Australia, off Brazil. So this whole area along the ocean is above average temperatures, um, and so that's we have upwelling here. So the water from under the ocean, deeper in the ocean, comes up, and so generally the ocean temperatures right along the shore become cooler because of this mass movement of water, and so that's the El Nino pattern. Then at times this motion ceases, or at least weakens, and so we get we remove that strong current, and generally the ocean temperatures are then below average in that region. Right? So it's a cycle. You go from El Nino to La Nina, back to El Nino, and so it cycles over time. Why there's that weakening is still something that many meteorologists question. But some of these patterns, even though they happen somewhere pretty far from us, do have a direct impact on our overall weather. And so meteorologists will look to these large-scale patterns to help make long-range forecasts that maybe perhaps will tell us whether we're going to have a snowy winter or not, among other things. So I hope this has helped. If you have any questions, feel free to leave me a comment or message me through Canvas. See you Tuesday.